So we looked at what multi-layer neural networks are. We had the input layers, we had the output layer, and we have the hidden neurons in between the input and the output. And we also know each and every weight has been, I mean, each and every network connectivity there has a weight associated with it. Example, I'm just writing a neural network structure over here. Okay, I have 3 inputs. I have first layer, hidden neurons, the second layer hidden neurons, and I suppose I have the output neuron. So I'll consider this the K output. Okay. So what I do here is I'll be connecting. Suppose I have the connectivity between these two like this. So I have the input neurons connected to the hidden neurons. Okay. There will be a weight associated with each and every input to the output. So here I'll consider this as W. Okay. Suppose I'll consider W 1 1 because from the first to the first it goes. Okay. Again from here to here it's again W 2 1. From here it is W 2 W 3 1. Okay. And similarly, now it has the second input, a second hidden neuron of the hidden layer, the third hidden neuron of the hidden layer. Okay. So these are the inputs. Each and every layer will have an activation and the pre-activation function. We told you, like this acts as a single perceptron. Okay. One neuron acts as a single perceptron, and we know a single perceptron has something called as a pre-activation and an activation function. Either I can use, what are the activation functions that we have seen so far? What are the activation functions that we have seen so far?
Sigmoid, step function, and logistic.
Exactly.
So not logistic.
Yes, we have seen the step function. We have seen the sine function or the sigma
Sine.
function. We have seen the sigmoid function. Yes. So what is my pre-activation? It is going to be the summation of all of the inputs, that is xi and the wi, right? So I have the pre-activation and the activation. So each and every neuron will now have a pre-activation and an activation. So every neuron will have this. Okay. So from the input also. So now I have all the input neurons. I'm passing it everything. So I'll just consider that maybe these are all connected as well. And from here, all my output neurons are connected. Okay. This is basically how my multi-neural network looks like. But from here, there is something which we again have to look at for. There is a BIOS that has been connected to each and every hidden neurons. A BIOS. So I'll consider this as B1, B2, and B3. What will be the total number of weights for one particular layer? How do we consider that? For this particular layer, let me just consider, for this particular layer, these 3 neurons, okay, what are the number of weights? How many weights does this has? How many weights does this has? In your lab program, you saw that, right? You had a 3 cross 3 matrix. How did you get that 3 cross 3? No idea? Okay. So normally these weights, I will be writing it as, to identify the number of weights with respect to one particular neuron, it is basically the total number of input neurons into the number of hidden neurons. You can see the total number of input neurons is 3. 1, 2, 3. What is the total number of hidden neurons? 3. I get 9 weights for one particular layer of 3 neurons. Suppose I have 1000 or 100 neurons, okay, the hidden layer 100 neurons and the input layer is 100. How much will I have? 100 cross 100 will be the total number of weights for that particular layer. Again, the weights, if I have to calculate for this, it's again dependent on the number of weights it has. Right now, the weights you can check 1, 2, 3, 4, 5, 6, 7, 8. One is missing because we have not given a connectivity. Okay. So basically it will tell you the number of weight assigned to it. So this is going to be the weights. And I told each and every hidden neurons will have a bias attached to it or associated with it. So the bias, total number of bias to calculate B, we'll be basically using the number of hidden neurons. This is very, very important to understand what will be the number of weights, what will be the number of bias that is attached or that will be utilized in the multi-layer neural networks. These are certain very important points to be understood. Okay. So beyond this, if we go ahead, if we start, why do we use backpropagation? Any idea? Why do we use backpropagation over here in the multi-layer hidden neural networks? We have seen what
To adjust the
backpropagation.
weight,
Why do we have to use backpropagation?
to adjust the weight.
Any idea? Okay, I'm traveling with one of my friend, a close friend of mine, where I have to reach the airport within the given stipulated time. Okay, I'm gonna drop him. He has to fly. Okay, so I'm gonna drop him to the airport. If I have to drop him to the airport, I will be looking at the timelines, okay, because I have just 1 hour to drop him to the airport and I'm still in the outer end of the total opposite end to the airport. What do I do now? Yes, what do I do?
Backtrack?
Yes, backtrack, fine. But before that, what do I do? This is just an example now. If I have to drop one of my friend to the airport and I just have 1 hour time, what will I do? Now I'm in the car, I've started to drive. What is the first basic step that I do? Will I go ahead with the normal route or will I take the shortest? Because I have to reach in time there.
Take the
Give
shortest
me the
route.
answer. Would I take the shortest route or would I take the normal route to reach where I know I will not reach within an hour? So what will I do? Wouldn't you take the shortest route? Zoom back. Okay. So we're going to take the shortest distance. So basically the similar thing applies over here. Rather than traversing and calculating all the weights for each and every neuron in the layers, okay, each and every neuron, obviously you have to update your weights. When I tell backpropagation or when I tell converging to a solution, okay, I have to come up with this weight matrix. This is very important where I have to have the values for each and every weight within that particular layer. So this is for first layer. Again, I'll have the similar one. I have to calculate for the second layer. And I know I have to calculate all of these weight matrix accurate. We have already seen the example of how do we update weights with respect to a perceptron or a multi-layer neural network. So each and every time you have to update a weight for each and every data point that is given to you. So every data point I have to calculate this, I have to update the weights, right? So it is time consuming. Yes, a lot of calculations involved into it. We have to optimize this weight calculation. That is, optimizing. The main usage of backpropagation is, which is commonly used most of the time, we normally tell that we have to have a gradient descent optimization algorithm. The weights are to be adjusted in such a way that there should be an optimization happening with respect to, so that we converge to a solution faster, or we converge to a solution with a less calculation. Okay, so that is the main usage of backpropagation. If someone asks you why backpropagation is required, please do tell that it is something which is very useful for the gradient descent optimization algorithm. We have, what is gradient descent? Basically updating the weights. So when I tell updating the weights, we have to make sure that we have to have an optimized weight updates to be done such that we converge to a given solution, or adjust the weights of the neurons by just calculating the gradient value using the activation function. So this is about backpropagation, why it is required. Now let's see how do we really trace these backpropagations, and how do we make the calculations go a little easier. Okay, I'm going to clear, I'll rewrite the diagram. Okay, so I have an input X, I have 3 hidden neurons in the first layer, 3 hidden neurons in the second layer, and I have my output layer. Okay, each and everything is connected. Yes. So this is my output. From my output, what do? We normally find the loss function. If we remember the example with respect to virtual lab that we consider, we first calculated the output with respect to X and weight. We multiplied the X value and the weight matrix. So the weight matrix was 3 cross 3 and the X value was 3 cross 1. We multiplied it, we got a single 3 cross 1 matrix where we applied the signum function to it, the sign function, where we got the values of it, right? And from here, what did we do? The next step was we calculated we had the output value. So this is our output value. We had the target value called as D. So we compared with these two. Wherever we observed the difference in the output to the target, we updated the weights using the perceptron training rule, which is W1 of new is equal to W1 of old plus the learning rate into T minus of O into Xi. Right? This was the perceptron training rule that we used and we updated. So we used to update each and every weights, and finally we used to get the complete weight matrix for all the neurons. So it was 1, 2, 3. That is with respect to the weight 1, with respect to the neuron 2, with respect to the neuron 3, we were updating the weights and we were calculating the next data point. So what is that basically we did? We identified the loss function over here. So the loss function, I'll just write it as ED, the training error, or I'll just write it as L of theta. So this is my loss function. We already know. How did we do? We got it through the output. So this is my output, and ED, I performed the perceptron training rule. So this is the visualization part. I've written it to the right hand side. Now the same thing, I'm going to apply it onto my left hand side of the figure. How do I do it? So it has an pre-activation and an activation. So pre-activation and an activation function. Each and every hidden neurons also have that. So let me just consider this part. This is my input. Now what I do, I will write this as H1, hidden layer 1, hidden layer Okay, each and every layer within that. So when I tell H21, H22, H23, okay, H12, H11, this is my first hidden layer, second hidden layer, and the weights. So what I do over here, I will write the activation function associated with it. So let me consider this as the pre-activation function H11, the activation function. The pre-activation function, I'll write it as A11, A12, A13. Okay, again here A21, A22, A23. And I know this is the weight of that. Okay, each and everything is associated with the weight. And I'll write the output, or I will write it as y cap, because this is my predicted output. My target output is different, but this is my predicted output. I will write it like that. Now, if I have to backtrack it, backtracking it is identifying its paths. What I'll do is I will first consider the center path. Okay, from the loss function, I'm highlighting it in red. Okay, this is the path that I have to backtrack it, and I have to come here. So I have to backtrack it and come here. Okay, so now backtracking, what I do is every time what I have to do, let's consider from the mission perspective. When I start from the mission perspective, first it is calculated the loss. Obviously, I know my loss is 1 by 2 summation of k is equal to 1 to n, how many ever it is t minus of o into xi. This is my loss function. Okay, so I have calculated my loss function. From the loss function, I have to again backtrack it, come to the path over here, which is nothing but till here, y cap. Okay, so this path is ready. From here to here, this is ready. Now what I have to do, first operation is done. Then the second operation will be something like from here to here. Let me write that in the statement. So what I'll write, L of theta with respect to, because I'm updating my loss function with respect to the weights. Okay, so I'll write it L of theta divided by the loss with respect to weights is equal to, the first one I will write it as L of theta by y cap, because from here to here is what I am concerned about. So I will write it as y cap into, okay, delta y cap divided by, I want the next point is here. This is my neuron. I want it till from here to here. So y cap into H22 delta H22 will be my next path. From here again, if I go delta H22 divided by, it has to come to this point. Okay, so I'll write it as delta H12. Again from delta H12, it will be going towards delta X. This is how I have to backtrack from the machine learning perspective. Like I have given a system, I have to come back, I have to calculate its weights. Now just see, I have suppose changed my path, the other path. I have to update a weight of the other path. I have to go ahead identifying this path. Should I be again recalculating each and every step for my mission? Or since I already have this, I already have this path ready with me. I know the value of this path, so I can directly utilize it. I already know the value of this path. I can again utilize it. The only thing I have to calculate now is only this path and this path. If I calculate the values of that, I can easily take the existing values of this path, and I can perform the backtracking algorithm. I can update the weights, easily update the weights, less number of calculations. Suppose a similar one, I have to again recalculate another path. Okay, another path, I will consider a path like this. I want it, I'm going to go from here, from here, from here, okay, again from here. So in this case, the third step when I'm doing, I already have this, I've already calculated this. Only thing I have to calculate is this path and this path. Since I already have the other two values, which is stored in the matrix, everything will be stored in the matrix format, either in your MATLAB or it can be in your Python. These values are already stored. So I can retrieve the values from the database or the data set that I have or the data structure that I have. Okay, I can take these two values and I have to only incorporate these two. I'll finish the path. So my weight updates is actually decreasing. You're able to go ahead with this?
Yes, ma'am.
Okay. So this makes our work more easy and it helps us um, to avoid certain calculations because it is already pre-calculated. Since it is already pre-calculated, I need not again go ahead and calculate each and every step. Okay. So what I'll do is I'll make this more simpler. Each and every step more simpler. So how can I do that step more simpler? Is basically I will consider this step, whatever I have over here, the red colored line that I have, right, the path, I will make that into simpler steps. Like first step I have done this, okay. Second step what I'll do is I will perform an operation between these two, because between my pre-activation and activation itself there's one step that I have to perform. There is certain calculations that I have to perform. What is that calculations? I will perform the pre-activation using this. Pre-activation is nothing but the summation of xi into wi. I'll be performing this operation. Upon that, I will be applying my activation. My activation is nothing but the signum function. It applies, I will get my output. So for one particular neuron, I will have two operations that I'll be performing with respect to activation and pre-activation. So what I'll do, this step will form first. Again, I'll perform one more operation, which is my second step. I will perform the third operation over here. From the third operation, I'll again perform the fourth operation, fifth operation. Again from fifth, I'll perform the sixth operation. Then there will be seventh operation to my input. So I'm again making the entire bigger step, okay, into again one level smaller by writing it like I'll have L of theta divided by delta y cap. Anyways, my output is fixed. Okay, but from my y cap, I'm going to do the activation to the pre-activation. Okay, I will write this as delta y cap, and I've specified my activation as A31 because A22, A31. I'll write activation as delta A31. From delta A31, that is the pre-activation, I'll go towards delta H22 till here, okay. Then again from delta H22, the activation function that I'm performing is delta A22. Again from here delta A22, the next operation that I'll be performing is with this, so it is going to be delta H12. From delta H12, I have an activation function delta A12. So from here to here I finished, and again I have to retrace back to x, so it is going to be delta A12 divided by delta x. So each and every operation, you can see I have 7 operations that I'll be performing here. The first one, second one, third one, fourth one, fifth, sixth, seventh. So when I do it in a little more smaller steps, what happens here is I have to backtrace any of the other path also. I have this and this value ready with me. I just have to calculate these two values, this value and this value. So these values are the value of the neuron. Okay, this is the value of the neuron which we normally calculated by using this function. So this will be normally the value of the neuron. I'll let you know what exactly the terms indicate, but we will be performing 7 simpler operations to backtrack one particular path. But when I perform that the values will really help me to calculate the other paths as well. So my weight updates goes more simpler. Rather than performing all the operations each and every time, we will go ahead with a simpler operation. I hope I have made this clear now. Yes? Can I go ahead? How do we perform backtracking? Am I clear?
Yes, ma'am.
Okay. So I'll just clear the board and I'll just give you a small insight of what we'll be deriving, how we'll derive the backpropagation algorithm. Okay. So I'll be writing it. Suppose let me consider I have one input neuron and the input neuron is X. I'll perform some operation. I have some other. Okay. I'll perform some operation. I'll get my OJ. I'll consider this is my J and this is my I. So I value, okay, and the Jth value, it has a pre-activation function over here and an activation function. Suppose let us consider the activation function is a sigma, okay, and these are my weights. So I'll write this weights as I and J, or J and I. From the jth to the I, I'm gonna write this, okay. The pre-activation function, there is again some other weights over here. So basically I'll write this as summation of xi into wj, or xi into uh, ij or ji, okay. I'll just write like this. So it's a summation of the inputs into the weights. So this, I will coin this as something called as net j. These are certain terms which are very, very useful for us for our derivations now. Please have a keen observation on this. I have the input neuron called as X, and the output value of it is going to be the value kth output neuron, or right now I'll consider the jth output neuron. So this is going to be the output neuron, the input neuron, and the weights associated with it. There is something called as a pre-activation. The pre-activation is basically summation of inputs into the weights. I will write this as net j. I have an activation function called as a sigmoid, which is applied onto it. Okay. So these are the input, very important terms: weights, output, net j. Okay. Now, if we start our derivation, basically our derivation for something like this, how do we start? The similar. If I have to backtrack from here, I have to backtrack from here to here. What will I basically write? Let me consider this is ED. I will write this, just check whether whatever I'm writing is right or not. Delta ED with respect to delta WJI is equal to delta ED divided by delta net J into delta net J divided by delta Ji. Does this seems to be right? What is delta ED here?
The loss function.
Yes. So from the loss function, what do I do? This is basically the loss function I will get. So with respect to, if I have to calculate with respect to this, what I'll do is the loss function with respect to ED. Here itself I'll get T minus of O into Xi. So this is what my loss function indicates. Target minus of output, the whole square. Okay. So when I consider this particular part, so from here to here is what I get it, but there's a very important term called as net J. So from here to here net J, I will write this. Okay. And again, from net J, from this particular, I have to get the weights part of it. So I will write net J into Wij, which I can easily write this particular term as delta ED divided by delta net J, directly this term, because it's a summation of with respect to this, okay, this particular part. So I can write this directly as xji or xij. This is a very simple term to calculate, okay, how exactly, one single neuron given to us, how exactly we can calculate the value of it is what we give it with respect to this. It's a very simple understanding. If I have to get these two parts, the first is I go ahead with the error function with respect to the net j. From this net j, I again go back to this. This is what our understanding is, and I have written it. When I already get to know this part and I have the weights is basically related to my xi value, I substituted that with a xi. We just have 1 minute time, so I'll stop the meeting and again I'll rejoin. Okay, I request everyone to rejoin.